This video is about how we reach the equations related to the brightness gain achieved by the actions inside an image intensifier tube. This forms part of the fluoroscopy system in the radiography department. The basic function of the intensifier tube was illustrated and discussed in an earlier video, which should be viewed before continuing this video. Following is a quick recap of the basic functions of the intensifier tube. The X-ray photons are emitted by the X-ray tube at a low dose rate, since it is a continuous beam of X-ray energy being generated. The first red layer on the left is the input phosphor, or fluorescent screen, which converts every X-ray photon reaching it into light photons. The second red layer is the photocathode, which in turn converts these photons into negative charged electrons. Those electrons are then converted back to light photons by the output phosphor layer. The last layer is the CCD sensor, which decodes the light photons into an electrical signal being sent to the monitor. During the transmission of the incident X-ray photon to the various layers within the image intensifying tube, the energy output is being increased through conversion of the energy into electrons and light photons, to ensure the maximum amount of information reaches the CCD and the final image being viewed on the monitor during fluoroscopic screening. Now we will focus on how these components relates to various equations. For every one X-ray photon reaching the input phosphor, 5,000 light photons are produced by the input phosphor surface. The 5,000 light photons then pass through the photocathode and form electrons. Here we see a decrease in the conversion amount, since for every 5,000 light photons reaching the photocathode, 150 electrons are produced. What is important to understand is the reason why we need to convert these light photons into electrons. Electrons can be accelerated by changing the voltage and current levels of the anode, thus speeding the electrons up and so creating an increase in energy. So although there is a reduction from 5,000 photons to 150 electrons, the gain achieved after the electrons reach the output phosphor is much more through this electron conversion process. The greater the acceleration of electrons using higher voltages, the better image intensification, or gain, occurs. As stated earlier, the 150 electrons which were released from the photocathode are now pulled towards the photoanode and onto the output phosphor layer. The output phosphor layer converts the electron beam to visible light photons. Flux gain is a term that refers to how effective the conversion from light photons to electrons to light photons is achieved within the image intensifier tube. If the flux gain is high, it indicates the electrons received enough acceleration and pull towards the anode and output phosphor surface, so that the gain of visible light photons by the output phosphor is dramatically increased. So, for every electron, 2,000 light photons are produced by the output phosphor. To recap, one single X-ray photon is converted to 5,000 light photons. This bundle of 5,000 photons are converted and reduced to 150 electrons when it passes the photocathode. These 150 electrons are converted to 2,000 light photons per electron, thus in the end a total gain of 300,000 visible light photons are produced. The conversion of one incident X-ray photon to 300,000 light photons at the output phosphor layer is part of the flux gain achieved during the conversion of the energy beam through the various layers of the tube. The ability to narrow down the electron beam at the photocathode layer to focus onto the smaller surface of the output phosphor is how minification gain is achieved. This is similar to a flashlight, which emits a light beam that is able to be visualized onto a smaller surface. The formulas and equations related to this process are: minification gain equals the input phosphor diameter squared divided by the output phosphor diameter squared. So for example, if the input phosphor diameter is 35 centimeters compared to an output phosphor diameter of 5 centimeters, the result will be the following. Flux gain equals the number of light photons at output divided by number of X-ray photons at input. So in our example we had a ratio of 1 X-ray at input to 300,000 light photons at output, thus a magnification gain of 300,000. Brightness gain equals minification gain times flux gain. Magnification gain is when the diameter of input phosphor reduces, the focus point moves closer to the input phosphor, and the resultant image at the output phosphor increases or magnifies.